So let's start again with our exponential growth model, where we have abundance on the y-axis, time on the x-axis, and the population that is growing exponentially. Now, remember, this is a section here that we're trying to understand how populations are regulated. So clearly they don't go to infinity. So how can we tweak this equation in a way that makes it not go to infinity? How can we add some elements to it, to this dn dt equals rn, so that when it gets to a certain level, it starts to level off? What is it that can we do? And the simplest way to actually do this is to change the rate of increase as the population starts to approach some level that, that is the equilibrium density of this particular species. So let's define this as some abundance number, and we're just going to call it k. And we can modify the exponential growth equation so that when the population is below this number, it will tend to increase. And when the population is above this number, it will tend to decrease. And when it's exactly at the level k, the population won't grow. So this basically has the effect of changing that intrinsic rate of increase as a function of the population size. So populations that are far away from k are going to grow quickly, but populations that are near k are going to grow slow, and populations that are right at k are going to grow not at all. And the opposite happens when you're above that number. They decrease until you get to k. So here's one very simple modification that people have made to this equation, which is by adding this little control term, the k minus n over k. And we're going to explore this in a minute, but the form of this equation here, this is the control term right here, that basically modifies the potential for growth. You can think of it as a number that goes between 0 and 1, and it tells you whether the population is growing very little or near its maximum potential. And the maximum potential is r. And this form of the equation is what we often refer to as the logistic equation, the logistic model of population growth, because it has this S-shaped logistic curve when it's growing from low numbers to high numbers. And we're going to explore what this looks like, the behavior of this in a second. So one way to explore the behavior of these models is to ask yourself what happens when the population has certain sizes, certain characteristics. So here's our logistic growth model again, which has that extra k minus n term. And one question to ask is what happens when the population is 0, when there are no individuals there? Well, again, this is pretty trivial. You take 3 terms that are multiplied by each other, and when you multiply them all together, if any of those terms is 0, then you're pretty much got nothing. So the population is not going to grow when there are no individuals there. All right, not that interesting. All right, so how about the situation where n is very small, but not 0? So like 1 or 2 or something like that. Well, if that's the case, then the rate of growth is going to be dominated by the k term. That is to say, if you take k minus 1, which is the size of our initial population, then you pretty much have k over k, which is about 1. So this means that the r times n term is going to be multiplied by approximately 1. And therefore, what this means is that the population is going to be growing very similarly to that exponential growth when the population is very small, which is kind of what you would expect. That break term, the k minus n over k, is not really doing that much. It's very close to 1. And so again, you get that exponential growth when the population is very small. On the other hand, when n is very close to k, what this means is the k minus n term, n is very similar to k. And so the numerator of that is going to be 0. And so when you multiply dn dt, when you multiply Rn times something close to 0, you're going to get something very close to 0. So the rate of change of that population, sorry, these got crammed next to each other, the rate of change of that population is going to be virtually non-existent. So the population doesn't really grow when n is near k. So now recall, this is not the population size that we're talking about. We're talking about the rate of growth is going to be close to 0. In fact, the population size will be right at around k. So when you're at k, the population stays steady because it's not adding or subtracting any new individuals. And that's what dn dt really means there. So let's explore this in just another way. What is really going on to that rate of population change? So let's do a really quick rearrangement so that dn dt is expressed in a per capita way. So if you take dn dt equals Rn and you divide both sides by n, or this is the logistic form here, the k minus n. If you divide both sides by n, then you will have the per capita population growth rate, which is again 1 over n dn dt. And this is equal to r times k minus n over k. And we've just moved n from the right side to the left side by dividing. This is simple algebra here. We could rearrange this right side into this form here, which is r minus r times n over k. And that's just taking the r and multiplying it out and just doing some distributive properties. So if you squint really hard, actually maybe not all that hard, you might recognize that this is basically the slope for the equation of a line. Y equals mx plus b. I hope you remember that. And where b is your, I'm sorry I got cut off here, but where b is your intercept, in this case it's r, and your slope is negative r over k, and your x is your n. So just rearrange that mx plus b, there we go, rearrange that mx plus b into this form here, and you'll see that your b again is your r, your slope is negative r over k, or r over k, and your x term is your n. So if we were to plot this line out, here's the shape that it would have. The intercept is r, and so the y-axis here is the per capita growth rate. You got to remember that. Your y term is 1 over n dn dt. So remember, that's the equation for the line. This is the intercept, r, and the slope is, here we go, this is your y is 1 over n dn dt. Your x is n, all right? Remember, this is the per capita growth rate. And there we are. And I will let you figure out how to calculate the x-intercept, but the x-intercept turns out to be k. And the line that connects those two there has the slope of r over k, like that. And in fact, it's negative in this case because it shows it as negative above. So what's basically happening here is that as n increases, it moves more and more towards the right, the y term, the per capita growth rate, or your 1 over n dn dt, is getting smaller and smaller. And in fact, it starts at r, that is to say, it's exponential in growth at the very beginning, and eventually it moves to 0, which means the population's not growing anymore. And it does so when the population hits k. And that's exactly how we've designed this equation, is that when it gets to k, the population is no longer growing. So if the population n is below k, it grows until it hits k, and then it stops growing because our per capita growth rate has now been modified to be 0. Again, here's our graph of population size over time. And if the population starts below K, it initially looks like an exponential growth near the beginning. And then the per capita growth rate gets smaller and smaller until eventually it peters out. On the other hand, if the population size is bigger than K, then the per capita growth rate is negative. Look at the equation a couple minutes back and that graph that shows that the per capita growth rate is negative. And therefore, the population will start high and eventually get smaller. So this is one way in which this population, we were able to create an equation that basically brings back the population towards some equilibrium. And the way it did this is by modifying the per capita growth rate in a way that was not constant, but it was dependent on density of the population. And this is an important concept of density dependence. And you might ask yourself, why am I spending all this time here? And that's because I wanted to show that this rate of population growth here doesn't have to be constant. It can actually be modified to be variable. And again, so that when the population is below that value K, the population is going to grow towards the right because the per capita growth rate is still positive. It's above that x-axis. I should have labeled it as 0 right there. And the population is above K, that 1 over n dn dt, the per capita growth rate, is negative, and therefore the population is going to get smaller. It's going to lose individuals. dn dt is going to be negative. And this concept of density dependence is actually very central to understanding the regulation of populations.